In this video, we're going to start looking at what are called separable differential equations. But first, do a little more substitution. First, this one, I'm going to make u equal to 1 plus e to the x. So then du is e to the x dx. And I'm not going to rearrange. You can see the e to the x dx is going to be gone. I'm going to replace that with just a du. So my integral becomes u to the 10th du. Well, the antiderivative of u to the 10th is 1/11th u to the 11th plus c. So 1/11th, 1 plus e to the x to the 11th plus c is my final answer. Okay, next. In this one, I'm going to make u equal to 2x minus 1. So then du is 2 dx. Well, I just have a dx, so I'm going to divide both sides by 2. Okay, so I'm going to have 1 over u multiplied by 1/2 du. I'll bring the 1/2 up front. Just 1/2 like that. The antiderivative of 1 over u is natural log, so it's 1/2 natural log of u plus c. I'll replace the u. Like that. And there's my answer. Last one. We're going to make u 2x minus 1. So du is 2 dx. So once again, I'll divide both sides by 2. So my integral becomes u to the 100th power multiplied by 1/2 du. I'll bring that 1/2 out front. Let me also rewrite the bounds. Remember, this substitution 2x minus 1 is u. This is our key for getting the new bounds. In terms of x, the bound was 0, but 2 times 0 minus 1 is -1, so the new bound is -1. The other upper bound was 1. 2 multiplied by 1 minus 1 is 1, so that is my new upper bound. Okay. The antiderivative, well, we raise the power and divide, so it'd be 1 over 100, but remember it's being multiplied by 1/2, so it's going to be 1 over 202. Excuse me, it was 1 over 101 plus, nope, there's no plus c, it's definite. Excuse me. And we're evaluating at 1 and -1. Well, if I plug in 1, I get 1 over 202. If I plug in -1, I get -1 over 202. So I get 2 over 202, which is 1 over 101. And that is the final answer. Separable differential equations are ones that are implicit derivatives that we actually have the ability to, through some algebra and some calculus, get back to what the original function might have been. So for example, this first one, we've got dy dx is equal to x multiplied by y squared. Well, there's really 3 steps here. The first is separate, the second is integrate, and the third is solve for y. So the first thing I'm going to do is separate, which means I want all the x stuff together. So I'm going to multiply this side by dx. Well, now I want to move the y. So I'm going to divide both sides by y squared. So I'll write 1 over y squared here. So now what I've got is 1 over y squared dy equals x dx. So I've separated. The y's are on one side, the x's are on the other. Now I integrate. Well, the antiderivative of x is 1/2 x squared plus a constant. And the antiderivative of y squared, remember, you could think about this like it was y to the -2nd. So you'd raise the power and divide, you'd have that. Now you could put a plus c here, but, you know, negative y to the negative first plus c. But remember, you are going to try and solve for y, so when you subtract the c, you'd have a constant minus a constant, which is just another constant. So I'm not even going to bother to write that quite yet. Okay, now, the other thing I should mention is we have been given a point here, you know, x is 4, y is 2, so we need to solve for the constant. We can do that any time that we deem to be easiest. I mean, right now we've got the constant right here. We could certainly, you know, we've got negative 1 over y equals 1/2 x squared plus a constant. We could plug in 2 for y right now and 4 for x and solve for what the constant is. What you'll see here, you know, negative 1/2 equals 8 plus c. The constant is negative 8.5 or negative 17 halves. Okay, so you could have solved for that right now. So now I'm going to take this, I'm going to go back up here, I'm going to say, okay, negative 1 over y is equal to 1/2 x squared minus 17 halves, like that. Another way you could look at this would be just, you know, x squared minus 17 over 2, since it does have a common denominator. All right, now I need to, first of all, get rid of the negative. So multiply everything by negative 1. It would do that. It would change the signs. Then I need to get y equals, so I flip the left side and the right side. And there it is. So separate. I did that up here. I got the y's on one side, the x's on the other. I integrated each side separately, and then I solved for y. So I had to do a couple things here with algebra, you know, to get the constant and then get it to just be a y equals. This is the original equation. So this one, okay, dy dx is y minus 3. So let's start with rewriting that. This one always looks a little tricky, but if you look at it this way and you think, I got to multiply by dx, now it actually looks a little bit easier because you think, well, I need to get rid of this, so I need to divide by 1 over y minus 3. Okay. The only way to separate is through multiplication and division. At this point, you don't really know how to do anything else. All we have left here is a 1. So now we integrate. The natural log of y minus 3 is equal to x plus c. Again, you could solve for the constant right now. I don't know that it would be easy to solve for it right now. Well, actually, I guess it probably would be. Okay, let me do it. So the natural log, let me plug it in. So 4 minus 3 equals 1 plus c. Well, the natural log of 1 is 0. So c is negative 1. Okay, so when we go up here, now I got to solve for y. The natural log of y minus 3 equals x minus 1. All right, so to get rid of natural log, I'm going to take e to both sides. So I have y minus 3 equals e raised to the x minus 1 power. Then I would add 3 to both sides. Now you could be done right here. This actually looks pretty darn good to me. You could also split this exponent up. You know, you could have it be like e to the x divided by e to the first, or you could write it as e to the x multiplied by e to the negative first. And you could do that if you wanted to, but you know, you could also, this doesn't actually look too bad. Right like that. Okay, let's do this very last one. I wanted to point out here, we've got e to the x plus y. So you could write that as e to the x multiplied by e to the y, right? When we add exponents, we're multiplying the bases. You know, it's like x squared multiplied by x to the 8th is x to the 10th. When you multiply the bases, you add the exponents. So these two things right here are equivalent, but it makes it easier then to see that, you know, you're going to multiply by dx and divide by e to the y, like that. So you have 1 over e to the y dy equal dy equals e to the x dx. Okay, so we separate it, we integrate. All right, well, this, of course, is just e to the x plus c. I want you to think about this. This is the same right here as e to the negative y power. So the antiderivative of that would be negative e to the negative y power, like that. So again, you could solve for the constant right now, or we could even do it. I'm going to do it a little bit later this time, okay? I'm going to start solving for y. I'm going to start with that this time. So I'm going to change the signs on everything. Now, a constant is still a constant, so changing the sign on a constant, you could have written minus c. I'm going to choose not to. So we take the natural log of both sides. So we'd have negative y equals the natural log of negative x, e to the x plus a constant. And then, of course, we change the sign again. So negative e to the x plus constant, like that. And now, you know, you could solve for y. I'm kind of running out of room. You could solve for y here by plugging 3 in. You know, 3 equals the negative natural log of e to the 0, so 1 plus c. You could solve that and get the constant. I'm actually going to stop there. But the big thing is it's always the same 3 steps. You separate, y is on one side, x is on the other. You integrate, and then you solve for y and the constant. And that's it.